Welcome to week 7 of our journey into digital IC design with Dr. Mark Narden. This is class EE 423 at Oregon Tech. In this week's set of lectures, we will be going through two main topics. The first one will be going into more detail on developing more complex CMOS logic gates. And in the second part, we will be going through alternative forms of logic, such as pseudo-NMOS, domino, and others. And so I'll present here the outline for this week. So first we'll start with the concept of bubble pushing and trying to minimize the logical function down to certain gate types and creating new gates. Going into compound gates that are doing functions more than just a simple NAND or simple NOR. Going through logical effort examples for these more complex gates. Then input ordering, talking about asymmetric gates where we no longer have everything totally symmetric in terms of all of the inputs. Talking about skewed gates, where we might be more interested in the rising delay than the falling delay or vice versa, and determining the best PN ratios to use for your gates. Let's start this week with an example of creating a more complex logic gate. So up at the top of the foil here is some RTL or Verilog code for a mux function. So we have three inputs. S is our select, D0 and D1 are our data inputs, and our output is the value of Y. The assign statement there, the Y is equal to, in effect, if S, your select, is true, you want to set Y equal to D1. If S is not true, or a 0, you want Y to get the value of D0. And so that's how you read that particular assign statement. So first, sketch a diagram or a design of this function using just AND gates, OR gates, and NOT gates. So pause here and do that, and then continue on after you've done that. So we could do that using two AND gates followed by an OR gate. So the AND gate in the lower left is saying if S is true and D1 is true, you get a 1 value out. The next AND gate is if S bar is true, so if S is not true, then you effectively, and D0 is true, then you get a 1 value out. So the way those two ANDs are working is if S is true, then the value of D1 goes through the AND gate, because if D1 is 1, 1 goes out, D1 is 0, 0 goes out. And the same thing with the other AND gate if S is not true. And then we take the resultant value of those two AND gates and OR them together, and that gives us the function above. So let's follow that example with example 2. Sketch that same design using NAND gates, NOR gates, and NOT gates. And assume that we have, like we did with the previous example, we have both S and S bar, S not, available. So pause here and show how you could do that with NAND, NOR, and NOT gates. So now that you've tried it yourself, we'll go through what we could actually design here. So here it looks very similar to the previous design where we had two AND gates followed by an OR gate, but since we're using NAND gates, we have an AND NOT at each of the AND gates because it's a NAND gate, and since we want to follow that by an OR function, we can do a NOT OR. And if you remember that basically the NOT function at the beginning or at the output of the AND gate, so the NAND gate has the NOT function, the NOT OR is effectively a NAND gate, if you remember from De Morgan's law. So we're using two NAND gates followed by a NAND gate, but we're showing it as its alternative logic of NOT OR. And effectively, those bubbles, the bubble at the output of the NAND gate and the bubble at the input of the NOT OR, kind of offset each other. So this is equivalent to AND gate followed by OR gate. So if you don't quite catch that, you can back up to the previous foil and go back to this one and see that this is the equivalent of AND gates followed by an OR gate. The previous two examples bring up the topic of a term called bubble pushing. So what we can do is we start with a network of AND and OR gates, then we convert the AND and OR gates to combination of NAND gates or NOR gates plus inverters. And then we start pushing the bubbles around and using De Morgan's law to try and simplify the logic into a lesser number of gates. So let's take a look at the example one. When we started with, if we look below at the figure A in the kind of upper left of the four different circuit diagrams below, we started with two AND gates followed by an OR gate. Now if we replace the AND gate, each of the AND gates with a NAND gate followed by inverter, we now have, and the OR gate with a NOR gate followed by inverter, we have the circuit as shown in the B, so the upper right of the four circuits below. And so we have AND gate or NAND gate followed by inverter, and then below that another NAND gate followed by inverter. The outputs of the two inverters are going into a NOR gate followed by an inverter. Now of course that's 2, 4, 6 gates. We want to try and minimize that as much as possible. So when we take that and go down to figure C, or part C of the figure in the lower left, what we can do is we can replace the inverters that we've drawn with bubbles that get attached to the NOR gate in front of the inverters. So the inverters following the NAND gate will take those inverters out and show them as bubbles attached to the input of the NOR gate. So now we have a not NOR gate. And then finally, so that gets rid of quote-unquote two inverters from our logical function. And then finally, in the lower right section, we take the inverter at the output of the not NOR gate and combine the bubble of that inverter with the bubble at the output of the NOR, and now we have a not OR gate. So I kind of over the years just do this in my head, but this is a way of showing how it kind of logically flows. And you can do this in stages, or as you get better at it, you start, getting good enough to do it in your head. So that's how we transferred from the example A to example B, or example 1 and example 2 of the previous two foils. The upper left A down to lower right D, we get two NAND gates followed by a not OR, which again is a NAND gate. And you can see that depicted in the very upper right, where the bold arrow showing that a NAND gate is the equivalent of a not OR. So if you didn't quite catch this, maybe go through the foil again, but hopefully this makes logical sense to you. Let's do a third example now and sketch, says sketch a design, sketch the same logical function that we did for the previous two examples, but using a single compound gate followed by a single NOT gate. And again, assume that you have both S and S bar available. So pause here. If you need a little bit of a hint, some of you might have used this compound gate or something like it to do an XOR function in the past, but go ahead and either sketch this more, not transistor level, but sketch this at gate level, what you would use for one compound gate followed by a NOT gate. So pause here. So the design we would have is a compound gate that does the AND OR function all in one gate. And again, it's always inverting because it's single compound CMOS gate will come out as a inverting function. So we have D1, S1, and ANDed together, S bar and D0 ANDed together, and then those NORed together in one compound gate, followed by an inverter, give us a AND OR function. And you can map out what the compound gate would look like in transistor level yourself, but I'll show an example of that in the next foil. Now that you know a little bit of basics of creating more compound gates and more complex compound gates, let's go into computing the logical effort of compound gates as opposed to the simple gates that we've done so far. So just as a review, the unit inverter is just an inverting function, and that is our basis of our unit delay. And so a unit inverter has a logical effort of 3/3. It's normalized to itself, and so its logical effort is 1, and its propagation delay is also 1. So let's go through a few more complex compound gates. So if we look at the next one from the left column, so the next column, we have a function of A and B NORed with C. So that combined in a single gate. You can see the symbol diagram for that in the second row. In the third row, we have the transistor level diagram where A and B, so for the NMOS devices, we have the A transistor and B transistor in series with each other. Since it's NORed with C, those two are in parallel with C, and then it's the flipped version of that on the top. A and B are in parallel and they're in series with C for the PMOS devices. And so if we look at the logical effort for each input is now going to be different. So in our previous gates we had kind of symmetric inputs where each input had the same logical effort to it as the other inputs. Now when you get into the compound gates, that's not always going to be true. So if we look at our A input and we need to sum up the total capacitance of the A input, we have a PMOS device of size 4, NMOS device of size 2, so we get 6, and then we normalize that by dividing it by 3, so we get 6/3. For the B input, it's the same as the A input. We have a 4 plus 2, 4 for the PMOS, 2 for the NMOS, and so we have 6/3 is the logical effort. And for the C input, we have a 4 size PMOS device and a 1 size NMOS device, so we have 5/3. And then for the propagation delay, we have to sum up the total capacitance on the output Y. So we have 1 PMOS device of size 4, and then 2 NMOS device, one of size 2 and the other of size 1. So we add that all up and we have 7. Normalized against the inverter is 7/3. So let's go through the other two. If you want to pause here real quick and try to figure out what these values are for the other two, and pause, and then I'll go through it myself. So now that you've paused and figured out for each of the other inputs for the other two gates, the logical function for the next one is the gate that we've been looking at, or the logical function that we've been looking at for the previous few examples, A and B NORed with C and D. So if you go through this gate, the A, B, C, and D inputs are all effectively the same as each other as far as size goes. You have one PMOS of size 4, one NMOS of size 2, so it gives us 6/3 as our normalization factor, and so all of them should be 6/3. So I'll go through that quickly, and the value of P is the total sum of capacitance on our output Y. So we have two PMOSs of size 4, two NMOSs of size 2, so that gives us 12, and 12/3 is our propagation delay. Going on to the final, more complex gate, where we have B or C ANDed with A, and then that is NORed with D and E. And so that complex function, the sizes are down in the bottom. If we go through for A, we have size 3 PMOS, size 2 NMOS, so we have 5/3. For B, we have a size 2 NMOS and a size 6 PMOS, so that will be 8/3. For the input C, it's the same as B, so we should get 8/3. D is also the same, but it's a slightly different series device, but it's a size 6 with a size 2, so it's also 8/3. And E is size 6 and size 2 as well for 8/3. Then our propagation delay will be the output node Y is connected to two size 6 PMOSs and two size 2 NMOSs, so that gives us 16/3. So you can see each of these has a very different function to it, but it's relatively easy to come up with the logical effort and the propagation delay to go through with our examples here. So if you didn't understand all of this, I'd suggest making sure that you go through this slide again so that you do understand it. This is the basis for a lot of trying to minimize your logic and figure out how to minimize your time delay through more complex logical functions. Let's go through another example here of this same function that we've been using for the previous examples. And we want to look at a multiplexer that has, we want the multiplexer to have a maximum input capacitance. So the capacitance that is supplied to each of the four inputs, S bar, D0, and D1, is a maximum of 16 units on each input. But we need to drive a load of 160 units at the output. And we want to estimate the delay of each of the two different designs. So if you remember from last week's set of lectures, we have a variety of different values that we need to look at in order to get our overall delay. And that is based on our path electrical effort, the branching that goes on in the design, the total number of stages that we have, and the parasitic delay, and all of these other parameters. So let's, if you want to try going through this yourself to begin with, go ahead and pause here. Otherwise, if you need a refresher, we can just start in on it now. So it's up to you. So let's start going through the various different values and parameters and compare the delay of these two different designs to each other as far as which one would potentially be the minimum delay. So to start with, both of them have the same values for H, B, and N, where again H is your path electrical effort. The path electrical effort, keep in mind, is based on the capacitance at the output to the capacitance at the input. So in this case, we said we need to drive an output load of 160, and we have a 16 units of load at our input is the way we defined this to begin with. So our path electrical effort is a value of 10. For branching, you can see in both designs we don't have any side branches. So our branching for each stage is 1, relatively easy. Number of stages, capital N, is in both cases. The number of stages is 2. So these values and these parameters are shared between both designs. Now let's start going through the parameters for the design on the left. So when we start out and we want to know our path delay, or sorry, I should say our parasitic delay through the path. So path parasitic delay. What we need to do is do the parasitic delay through each of the gates and add them together. So for a NAND gate, and again the not or is a NAND gate, so the NAND gates have a path delay of 2 for each individual one, so the overall parasitic delay for the path, capital P, is 2 plus 2 equals 4. Now for the path logical effort, we take the logical effort per stage and multiply them together. So again, if you go back to the table that was presented, or if you remember, a NAND gate has a path stage effort of 4/3, and so the path logical effort would take each stage, multiply them together. 4/3 times 4/3 is 16 nights. Now the overall path effort is defined for a path, G times B times H. If you don't remember that, again, I'd recommend going back and reviewing from last week's set of slides. So G, we just calculated, is 16 over 9. B is what we calculated at the beginning of the number 1, and H we calculated at the beginning number 10. So we basically have 10 times G, so 160 over 9 is our total path effort. And then the next variable down there is the minimum effort that we can have per stage. And if you remember from last week, that is the capital F value to the 1 over capital N power, or the nth root of F. So we have 160 over 9. We have 2 stages, so n is 2. So we take the square root of 160 over 9, and we get the value 4.2. And then finally we can calculate our path delay, and our path delay is going to be capital N times the value of F there, the minimum. So we have 2 stages that each have a minimum stage delay of 4.2. We calculate those, multiply them together, and then we have to add the path parasitic delay to that. So we effectively have 4.2 times 2 is 8.4, and we add the value of capital P to that. So 8.4 plus 4 is 12.4 times our tau. So our overall delay is going to be 12.4 tau. Now let's go a little bit more quickly through the next design. So the next design, we have our capital P is the first stage there, has a parasitic delay of 4, and you can go back in the previous foils in this lecture to see that we calculated that as 4. The inverter is a delay of 1, so the parasitic delay is 4 plus 1 equals 5. For the path logical effort per stage, the first stage is 6 over 3, second stage is 1, so we just get 6 over 3, or a value of 2. the F is G times B times H again. So we take G is 2, H is 10, and B is 1. So we get a value of 20. Then here we take the square root of 20 and get 4.5. And the value of D is going to be 4.5 times 2, or 9, plus the value of P is 5, so we get 14T out here. So you can see the design on the left could be a little bit faster, maybe not quite, actually I guess about 10% faster depending on how you look at it. So it is something that we could make the one on the left be a little bit faster than the one on the right. Continuing on from the example we just did in example 4 in the previous foil, here I'm showing the transistor level diagram for the two designs we went through in the last slide. So on the left we have the design that shows two NAND gates as our initial inputs, and the outputs of those two NAND gates go to the third NAND gate, which gives us our output Y. And what we want to do here is annotate these designs with the sizes of transistors that will achieve the minimum delay that we calculated in the previous foil. And again, on the right hand side we have the complex gate that it did the NAND NOR function all in a single gate followed by the inverter, and annotate that design with the sizes of transistors that you would need to do the same function and get the minimum delay again that we calculated in the previous slide. So pause here and attempt to do this yourself, and then I'll go through how you would do this myself. So let's go through first the example on the left. So for the example on the left, keep in mind we said the input on the very left hand side, we needed to have Cin equal to 16. That was given as a parameter of the design itself. So if the input is 16, keep in mind that since we have two NMOS in series with each other, the NMOS are going to be the same size as the PMOS. So if we have 16 and NMOS are the same size as PMOS, the left hand side would have size 8 for both the NMOS and PMOS transistors. Then we just need to calculate the size of the transistors for the final output NAND gate. So for this, if we go back in the previous week's lectures, when we're looking at sizing, we take our output capacitance that we need to drive. So the output capacitance was given as a value of 160. So we take that output capacitance and we multiply it by the factor of the stage logical effort. So the stage logical effort is small case g, and we take that value divided by the delay that we need. So that's the f sub hat function or value that we calculated in the previous foil. So if we take for a NAND gate, the stage logical effort is 4/3, and the delay that we calculated from the previous slide for f sub hat per stage was 4.2. So we take the 4/3 divided by 4.2, multiply that by 160, and we get a value of 50. So again, since for a NAND gate, two input NAND gate, the n sizes are the same as the p sizes, so we take the value of 50 divided by 2, and each of the transistors is size 25. So that gives us what we have in the circuit there. Now when we look at the circuit on the right, we want again the input size for the gate is going to be a size 16. So we need to pick values of NMOS and PMOS sizes that will give us a value of 16. Ideally, we would want the NMOS and PMOS to be a function of 2 for each other, or a ratio of 2. So ideally we would want either 10 over 5 or 6 over 12 in order to be balanced. But since we're trying to get a value of 16, a 10 over 5 would give us 15, and a 6 over 12 would give us 18, and neither one adds up to 16. So here they're just trying to balance it as close as you can get and stay with, you know, even integer multiples. So we get 10 over 6 in order to get the value of 16. So that's the only reason that that was done. In reality, you might decide that you'd rather do 10 over 5 and actually only have a value of 15 there, but we're doing 10 over 6 so that we get the exact value of 16. But for the next stage, we do the same sort of function in order to figure out how big the next stage needs to be. So we take the C out that we need to drive of 160. We multiply that by the combination of the stage electrical effort, stage logical effort, small g. For an inverter, that's 1. And the value of f hat that we calculated on the previous slide for this particular combination was 4.5. So we take 1 over 4.5 times 160, and we get size 36. So 36, when we have a 2-to-1 ratio of PMOS to NMOS, comes out with PMOS size 24 and NMOS size 12. So that's how we get these values out for, or how we would calculate it for each of these two different designs. And you can see, even though the design on the left is potentially faster by, it wasn't a whole lot faster, about 10% faster, when you actually look at the device sizes, you can see that the design on the right is a lot smaller total device size. And so if you were more concerned about the area that you're taking up than you are the absolute delay, you might determine that the solution on the right is smaller and more compact and fits in the area, and you might decide to use that over the one on the left, even though the one on the left might be a little bit faster. So again, it's ways that you can trade off different parameters, speed versus area in this particular case. Depending on what is more important to you, you can decide on the two different designs.